Okay, good afternoon everyone, good evening from Australia. Welcome to part 2 of methodology of designing a winning buggy. My name's Glen Humphries. I was a design engineer at Edge Products. It's a company we do off-road buggies, small motorcycle powered buggies. And prior to that, I was involved with the University of Adelaide Formula SAE team. And if all goes well, I will be one of your design judges at ESI 2019. So jumping straight into it. If you haven't seen part 1 yet, head over to the ESI YouTube channel, have a look at that. Otherwise we'll jump straight in. We've got a fair bit to cover tonight, so away we go. Right, so we'll split it into 2 parts tonight. First one, we'll be looking at FEA setup, particularly some issues that have come up regarding how teams are setting up FEA and similar analyses, and how we can improve on that. Part 2 will then be looking at testing, validation. Once you actually have your component, what can you do with it to make you a better design engineer and more successful in the design event. FEA, justification and intention. So, long before we get to any of the nitty-gritty details of FEA, so when we're looking at loads and forces and meshes, we want to go right back and can we justify the FEA, and are we doing it with the right intention? Are we doing it for the right reason? So an FEA for the correct reason is essential to get the setup of your FEA right. It all needs to be about why you're doing this. So it must be based on a real-world question about the component under real-world usage. So it's not very useful to see FEA which is based on a component loaded or constrained in a way that doesn't reflect the real world and how we want to see that. So just having some technical issues. No, we're good. Sorry, anyway, back to it. So research and development engineering must start with a question and get to an answer. So if you're doing a sort of engineering where you've already got the answer and you're trying to get the question, you're probably doing forensic engineering. Okay, so that's when we look at a crash or an investigation of some sort, trying to figure out what happened. That's not what we're doing in these sorts of competitions. We're looking at research and development. So we're going to have a question about our component. Does it do this? Can it do that? How's it going to behave? And so the best FEA questions, they should start with the phrase, if I had this component in real life, I would want to test ... If I had my chassis in real life, I would want to test how it behaves in this way. If I had my suspension arm in real life, I would want to test the amount of load it takes for it to yield. It needs to be a real practical question like that. What frequencies in modal analysis? Excuse me, what deformation, what stresses when I support it here, when I push it over there, when I add this, when I remove that. We're always trying to base this on real components. And this happens when designers already have an outcome they want a certain result, and they set up their FEA to try and get that result. And so because the setup didn't start in the real world from a real world usage case and then translate into FEA, the FEA results are not going to translate back. So what we FEA algorithms, they're not a perfect computer version of the component you're trying to analyze. There isn't actually a chassis inside your computer being pushed and pulled. It's just a set of numbers and a set of equations which are trying to be that. They're pretending to be a chassis, and we're sort of pretending to push on it by putting numbers into those equations. Of course, the output means that your FEA results, they're just numbers as well. You don't actually output a bent chassis. It just outputs numbers, and those numbers are pretending to be an object shape or temperature or frequency or whatever other property you're analyzing. So the pretend value of the outputs is only as good as how well you can pretend to be the object in the first place. If your equations can pretend to be a chassis quite well and you give it good pretend conditions, then your outputs are going to be pretty close to real life, and that's what we're aiming for. So to put that point home, your FEA setup must always try to follow real object and real conditions as closely as possible. Okay, And this is a nice little test I like to tell students to see if they would really trust their FEA. So I want you to imagine a scenario. You've got a question about a component that you're trying to answer. Now, I've set up my FEA with inputs and conditions, which I think are going to give me a good result. I think that's going to do it. Now, imagine a scenario where I actually have a real copy of this component, a suspension arm or a chassis or a gear or whatever, and I give the real component to my friend, and I ask them to solve the same question that I'm trying to answer. And I don't tell him anywhere else, and off he goes. And I come back a week later, and he says, "Okay, I've made a real-world experiment. It's set up in my my workshop, and it just happens that his setup is identical to the way my FEA has been set up." And he says, "Well, this is a real experiment. It will give you real, accurate, useful information." And you have to ask yourself, if I saw this, would I trust his results? Would they be accurate? Would they be useful? And would they be relevant? Do they answer the question that I was trying to solve in the first place? If no, then your FEA setup needs to be more realistic. If you look at his setup and you go, the way you fix this component in your workshop means that the loads put on it are not going to be an accurate representation of the way it is loaded in real life. That tells you that the loads in your FEA need to be more accurate and more realistic compared to the way the object will actually be loaded. So that's a nice trick for seeing if your FEA setup is really accurate. Okay, FEA recipes. So FEA can be a bit like cooking. Often there are a lot of tutorials out there and a lot of really good FEA tutorials out there. And they're a bit like a recipe. You follow the instructions, you put all the right ingredients in, you don't add anything else in, and away you go. Now, these tutorials are really good, like a recipe, for discovering new ingredients and new techniques, things you didn't know before. They show you how to use them, where to use them, and you learn some new things. And having more ingredients for your FEA that you can use correctly will make it more realistic, it will make you a better engineer, and it'll make you a lot more flexible in solving problems. But there's a big difference here. A good recipe for food should always give the same result, but that's not what we want for FEA. Every analysis you do is going to be different. There are different components, different load cases, different scenarios, maybe even different materials. So you need to be creative. You need to have a bit of creativity in how you're going to solve these problems using the same ingredients that you've been taught from tutorials. And this is where it comes down to trial and error and learning stuff. So a good chef will experiment and they'll make mistakes. Every good chef has a long history of dishes that have been burnt or too salty or too runny or things that didn't work out and they didn't get delivered, but the chef learned something. And you should be doing the exact same thing when it comes to FEA. Rather than just treating it as a one-off tool that you apply to your component and go tick, that's that tick of safety we're trying to avoid. We're trying to actually learn things about this. So you should experiment with FEA. Try analyses that seem a bit unusual. If they work or if they don't work, learn why. Go beyond the recipe of tutorials. And this is why, even though half this presentation is about FEA, we're not really going to cover any direct recipes for how to solve a certain FEA problem, because that's not the point. There are lots of great FEA tutorials out there, written by far more experienced people than me, and they're really good for building up your toolbox or your ingredients for how you can do your own analyses, but they're only good to get the same result every time from those tutorials. You as an engineer, you need to go and experiment with things and try new stuff, and that's how you're going to build up a much stronger and more versatile analysis capability. And also be proud of the experiments which don't go according to plan. I've done lots of analysis of lots of different components. Some of them have gone really wrong. It's crashed or it's given me a ridiculous result. But they're mistakes that I made at a time when I could, the mistakes wouldn't have a huge negative impact. So the mistakes that I didn't make when I was working in a professional job or when there were lives on the line. And so the mistakes I didn't make when it really counted. Okay, and we'll just quickly spin through some of those ingredients. And again, learn more about these from the tutorials available on the internet or from your lecturers. They'll be far better at giving you a real in-depth look at each of these ingredients. But instead, I'm just going to quickly spin through them as things to keep in mind. These are things you should be looking out for and exploring. For simulation type, we've got this is your basic choice of the algorithm. Should be a static analysis, so we don't care about change over time. Should be modal, where we're looking for vibration to see if our component might shake itself to pieces. We're doing explicit dynamic analysis, and that's where we're doing very short-term, high-impact yielding analysis. And material properties, we want to make sure our elastic modulus, yield strength, density, are they non-linear materials? Are we looking at maybe even non-linear materials, but within their linear range, so we can treat them as linear materials? Or are we looking at things like elastomers or other non-linear materials like that? Mesh type, obviously you've got our three basic meshes: beam elements, shell elements, and solid elements. And it's important to understand the differences between these. Go out and research where you can save a lot of time and effort by using the right elements. And even within solid elements, you've got lots of different options, for example, tetrahedral and hexahedral. Mesh quality, mesh convergence, and mesh singularities, the black holes of FEA. Constraints, have you got fixed constraints, directional constraints, where it should be allowed to move in a certain direction. This is often one of the biggest mistakes made in FEA is components that are unrealistically fixed when they should have more relaxed constraints that will allow the object to take on the stress pattern that it will really have in real life. Remote constraints and remote forces. I've also got contacts, where we should be looking at how two objects interact with each other. And again, that's an underutilized part of FEA where it can solve some really big problems for you. Loads, obviously you've got forces, moments. We've also got things like remote forces, and that's where we have something attached to a component, putting a force on it from a distance. For example, loading up our upright using a force applied at the contact patch, rather than just pushing on our wheel hub itself. We push where the tire is pushing, and that'll give us our correct loading pattern. Model subdivision. This is another really powerful one that can help simplify your analyses if used correctly. So we can subdivide models for easier meshing. We can subdivide them for more accurate loads. Sometimes you see loads applied over a huge area, loads or constraints, applied over a huge area when really it should be confined to much smaller subdivisions of the model. And algorithm allowances, and this is another one that's often forgotten. Again, allowing for non-linearity. If we've got elastic material, like materials like rubber, or if we're looking at yielding, or even just large deformation, elastic deformation. And then convergence. So some algorithms will solve directly, so basically just solving the equation, punching out an answer. Other algorithms will try to converge using a numerical method, and watching that convergence and analyzing it can also be really important. So once again, I'm not going to give you a recipe for doing FEA here. That would sort of defeat the point. Instead, these are the ingredients that you should be looking at. If you're a chef, there's a big list of your basic ingredients you need to know about to be a good chef, and these are your ingredients you need for FEA. I will, however, include just one picture of an FEA. So what we've got here is it was a chassis analysis from 2014 Adelaide University Formula SAE car. As you can see here, we've got a beam analysis, and there's a point I want to make here. It's a chassis analysis, but it's also got the suspension in it. Hopefully we can see an indication on the screen here, where both front and rear suspension members have been modelled, and that's because the pattern of loading from the wheels to the chassis obviously goes through the suspension, and in a very complex way, in a way where it's much easier to simply model the suspension and include that in the analysis than it is to try and do that realistically using individual forces. It's almost impossible to go through and work all that out and apply it directly to the chassis. So instead we use more components in our analysis to add in and provide a more realistic loading scenario. FEA interpretation, so we've crunched the numbers, but we've got to remember, FEA results are numbers pretending to be an object's shape or temperature or frequency or some other property. They're only numbers, and the program does not know what answer you are looking for. You might know, oh yes, I'm trying to find the stress here, or the maximum deformation, or some other property. But the program doesn't know that. It's not going to find the right answer and throw it in your face. So we need to know exactly what we're looking for, and the other things we need to keep in mind while doing so. Often, people simply will look for, say, von Mises stress, compare it to yield strength, and the object passes, tick, great, everyone's happy. But in a lot of cases, that's not really accurate. And the first example of that is when we're more concerned about elastic deformation limits. So that's basically asking, is the component stiff enough rather than is it strong enough? So we're looking for deformation results, and all your FEA packages will be able to output that. And sometimes we might be looking at the absolute deformation, how far did it move through 3D space? Or other times we're just looking for 2D deformation. For example, I don't care how much it moved forwards or backwards, but I'm concerned about the up and down movement of a component, and so I can give me component it can break down the deformation into XYZ components. But a good example of this is, for example, some of our suspension components, or in particular steering compliance. As some teams know, if you make your steering too lightweight, it may not break, so it's strong enough, but it may be very compliant. It's very elastic, and there's a lot of elastic slop in the system. It makes it very hard to drive. So in the case of those components, making them stiff enough so they don't elastically bend during use is more than enough to make them strong enough. This is actually true for a surprising number of components in general engineering. For the most part, if something is bending to the point where it's about to yield, it's already deformed way past the useful point where we can use it as a component. So keep in mind that whenever you're looking at a component, yes, it may not be yielding, but has it already moved into a shape that's not acceptable for use? Number 2, yield strength. This is our more traditional one. And this is for components where they might be, they might be allowed to have a wide range of elastic motion, but we don't ever want them to yield. Once they yield, they're useless. So a good example of that is an aircraft swing. Aircraft obviously need to be as light as possible, and often you'll find that aircraft flex a surprising amount compared to the engineering structures we see around us, compared to cars or bicycles or other sort of vehicles. And it's basically because an aircraft is allowed to deform a large amount elastically. The wings can elastically bend up and down. The chassis, the fuselage, can twist and bend, and that's not so much a problem for an aircraft. Obviously, they don't want it to yield because then it doesn't work anymore. So in that case, we're just looking for yield strength. In other cases, we are concerned about yield strength, but the ultimate tensile strength might actually be a bigger priority. And one example of this is when looking at a roll cage, in the case of a severe collision where, excuse me for a second. So in a roll cage, in the case of a severe collision where part of the roll cage has deformed, but we still want to protect the occupant. Now, in most cases, a roll cage, you want it to be able to take a bit of knocking here and there and have no yielding. So that's when we look at our yield strength. In other cases, though, cases of a severe crash, yielding is acceptable. In fact, it's desirable. We want the cage to give slightly to absorb some of the impact and decrease the impact load on the driver. So yielding, not as much of an issue, but ultimate tensile strength, this is the point at which the cage rips open or completely collapses or breaks, and obviously we want to avoid that. So that's when we can start looking at materials that have perhaps a lower yield strength but a much higher ultimate tensile strength. And we're looking for that in our FEA if we are doing this sort of analysis. Now, obviously, the analysis for a crashing chassis under a yielding is going to have to be non-linear because we've got plasticity. And often von Mises may not be a suitable model for our ultimate tensile strength, depending on the material, if it's directional, and depending on how we're measuring ultimate tensile strength with including shear or as maximum principle, all that sort of solid mechanics stuff. So, interpreting FEA. All right, so those are our interpretations of FEA using stress and deformation, stress and strain. And often, like we've just gone through, that leads us to a lot of useful answers that may well answer the question we're after. But there is more to consider. There's a lot of numbers going on behind FEA, and some of them can be very useful for our analyses. For example, constraint reactions. So when we put our component into FEA, we constrained it at certain points and we loaded it at other points. Now, we might have put a lot of thought into our loads and maybe a lot of thought into how our constraints are set up, whether they're fixed or allowed to rotate or translate or whatever. But the constraint reactions basically form the other half of our equation. And any FEA program should be able to give you values for what the constraint reactions were. For example, if we have a chassis, it's fixed at a certain point, we push 1,000 newtons on it, we should get 1,000 newtons at our constraint, and possibly more reactions depending on moments and couples and that sort of thing. So have a look at your constraint reactions, pull them up out of the mathematical pile that's come out of the FEA, and consider, are they a realistic magnitude? Are we getting a constraint reaction of hundreds of kilonewtons, something ridiculous like that? Are they the correct direction? If I'm pushing up on a component, are its constraints pushing downwards against me, or are they also pushing up? And if so, we've obviously violated Newton's third law, and something's gone horribly wrong, so we need to look into that. Are there any zero reaction constraints? For example, did you constrain 4 points on an object, and then there's only reaction forces at 3 of them, the other one's basically useless? This tells us that either your constraint assumptions were wrong, and that point is not required, or it tells us that the algorithm has decided that that point isn't required when you actually know it is. So we need to look into that. And do your constraints match the real world? Do they generally make sense? For example, if we've got constraint at a bolt face, where the bolt should be pulling down on the object, we run our FEA, and it comes up with a output saying that the bolt is actually pulling up on the object instead of pushing it down. That's not real. That's not actually happening in real life. So you need to consider those things. Contacts, and this is another really important thing I wanted to bring up. And the picture we've got here is another one from the Adelaide Formula SE car. It's an upright. It's basically 3 components: a billet machined centerpiece, and then 2 billet machined components either side, the one on the back for the brake and the one on the front for steering. And analysing all these, they need to be analysed as one assembly. So effectively, we might constrain the 2 bearing mounts top and bottom, and constrain the steering mount. Excuse me. And then we put tyre loads on it and see how that translates into load throughout this assembly. And we can't realistically simulate only one of these components at a time, because they all move together, they all deform together, and they all transfer loads onto each other through these contact interfaces. So getting the results from these contacts is really informative, and it's really important, A, to make sure our analysis is run correctly, and B, to show us things we can learn about the question we're trying to answer. For example, how is a load distributed? Where we've got this brake caliper mount on the back with the 2 ears sticking up, bolts on to the back face of the upright. They bolt on over a large area, but it's not realistic to just glue those 2 faces together. Instead, we put a contact across them, we bolt them down with a preload, but then when we put a caliper force on there, is the load distributed all at one end? Is there a lot of compressive force at one end and not much at the other? Or is the caliper mount trying to lift up in the middle and putting a lot of bending stress at either end? And these are really important numbers that can can really tell us how we can improve our design. And also for contacts, should we include or ignore friction? That could be another really interesting one to go and research. All right, spin on to part 2, physical testing and validation. So hopefully part 1 has given people something to think about in terms of doing your FEA in a way which is actually really useful for the design of your vehicle and the design of your constraints. The design of your components. Part 2, physical testing and validation. Why validation is important. When I was a student, I hated the V word. It got rolled out all the time and it didn't seem useful. So I'm trying to turn that around. Why validation is important. Early stage designs, for example, if you saw our first lecture, the design of the vehicle began with some really basic bottom level numbers. For example, how long is it going to be, how wide is it going to be, but also some really early calculations like our suspension frequency, our spring rates, what sort of weight distribution, weight transfer we're going to have. We made these calculations, and sometimes we estimated numbers, and to be honest, sometimes we just kind of guessed them. And then our late stage designs, where we've narrowed the design down a bit and we're just trying to figure out components, for example, arms, uprights, the bearings that connect them, all those sorts of things. We try and specify those later in the design, but all of this stuff is still just theoretical. We've got a great design on computer. Our team of lots of people have spent a lot of time getting to this point, but it's all pretty theoretical. And all these theories are based on assumptions and estimations. Now, as an engineer, a lot of your job is to try and come up with good assumptions and good estimations. If I want a certain brake pressure, what size brake master cylinder do I want? And that's an assumption and estimation to get to that point. And as a good engineer, you should be able to do a pretty good job of that. However, we do get things wrong. At worst, a mistake in engineering obviously could lead to lost time, lost money, or worst case, a loss of life. In that case, we're trying to ask, how did it break? Why did it break? And which of our assumptions was wrong? If we take it that we never build a product that we know is going to break, so we always assume it was going to work in the first place, which one of those assumptions has gone wrong? Which one of our estimations of how heavy something's going to be, or how much it's going to accelerate, or what voltage it's going to put out, which one of those was wrong? But even say if it did work, if nothing breaks, everything goes well, but it's unvalidated, we haven't learned anything. If our estimations were correct, how correct were they? Excuse me. What could be improved? And are our methods transferable to other problems? And this is where the real engineering learning happens, is when we validate our assumptions and our estimations. And it's where we should really get the confidence in your design. Now, you can be nice and confident about design if you've done lots of driving, you've driven it for days and days and days and it hasn't broken. Okay, you're confident in the vehicle, but in the design itself, how do you know that you've reached the optimum vehicle, or at least a good approximation of how good that vehicle can be? So we'll start off with workshop testing. And there's an enormous amount of validation and testing and experimenting that can be done just in the workshop without splashing out on really expensive equipment. And this stuff's often pretty small scale in the sense of we're only testing one component at a time, or maybe 2 or 3. And it's really good for checking, for example, your FEA procedures. And so we can be either destructive or non-destructive. And we can have even really simple cases where, for example, we've got an upright. We know it's supported by a bearing at either end, and it's loaded by a hub in the middle. And we can build this, restrain it correctly. Don't bury it in concrete, but we bolt it in a realistic manner. And then we put a known load on it and measure the deformation. And that should immediately give you something that you can compare to your FEA. So you did put all these hours and late nights into doing the FEA and refining your mesh and ensuring your loads are correct, and then refining the component and pulling all the weight out of it. Great design. But like I said, it's all still kind of guesswork until you've just done something really simple in the workshop. The component under a certain load deforms by 1.2 millimeters. That compares to 1.1 millimeters on the FEA, and we're getting pretty close. So it's at least a quantifiable number that you can take on board when considering if your FEA is correct or not. So we can also do, for example, controlled simple chassis testing, probably elastic testing rather than destructive testing on a chassis, given how hard they are to make. For example, by restraining it in certain ways, putting known forces on it, and measuring deformation. And presenting this sort of data to a design judge is extremely valuable. It really makes the judge's day when you can bring actual real-world data that says these are the values that we get in our workshop. When we push this, we bend that, we twist this, we put pressure on this other component. These are the numbers we get. Here's our FEA. See how similar they are. And judges absolutely love that, because what you've done there is you've taken your theoretical estimations, your assumptions, they sort of fed into your FEA, which is, like we said before, your FEA is just pretending to be a component. It's pretending to put inputs and pretending to give you outputs, and you've made it real. So you've actually taken all the guesstimation and assumptions, things that you hope are correct but you're not sure, and you can say, here it is, here's the numbers, it's real, and we were right. And that's fantastic. And as a design judge, that's just wonderful. That's really what we want to see. And we want to see that because that's what industry wants to see. When you get a job as an engineer, that's what people need to see when you've come up with an idea for a component, whatever you're working on, aircraft or submarines or earth-moving equipment, and you say, here's a new component. It's based on estimations and assumptions. We analysed it. That was also based on assumptions. Here's the real component, and it matches what we've done. And that's just fantastic. That's what makes all the senior engineers and your managers really happy. So validation tells you where your FEA is acceptable and where it needs improvement. So your FEA may also be, it may match the real testing results in here, here, and here, but some other part of it is wrong, or it's not as right as all the other bits. So that tells you where your FEA needs a bit of work. And again, that's great feedback to tell you where to focus your refining efforts. Okay, other workshop experiments. So we'll sort of move a bit beyond validating FEA in the workshop here. And we'll just excuse me for a second. Okay, we're good. And move into other workshop testing and experiments we can do. And again, these are all great stuff to show judges. We love seeing this. So this is for validating more of component choices and perhaps component setups when you're able to tune a component itself. So for example, the estimations and assumptions in our design choices, it's not just a matter of estimating FEA forces. We also estimate bolts that are going to be strong enough. We estimate bearings that will last long enough. We estimate rod ends that are going to carry the loads we need. And we estimate, for example, shock absorber setup, valving, which is going to reflect the actual physics numbers that we require of the system. And so it's really pretty easy to do destructive testing for these sort of things. Now, some destructive tests can be a bit dangerous, so of course, stay safe when you're designing these things. There can be a lot of force involved. But for example, if, say at competition, you're using a certain size rod end for a certain job, and you can say to a design judge, we know how much force is on this. We took one of these rod ends and we put load on it, and it failed at such and such a force, which we actually tested, we have the results for. Therefore, we know our safety factor. That's brilliant. That's fantastic. That's all you need to show for that. Similar with bolts and pins and bearings and that sort of thing. Another one is a shock dyno. Basically, this is for measuring shock absorber responses. What's its actual dampening in terms of newtons per meter per second, etc., etc. Effectively, you can do something really simple here. Just a basic rig with a falling mass. Maybe it falls on a long arm to control it. It falls onto the shock absorber, or the shock absorber falls onto it, depending how you set it up. And you can get reasonably accurate measurements off of this with something just as simple as a video camera and a scale in the background. Okay, this is not super precise NASA level science, but often here with something like a shock absorber, you're just trying to get within the ballpark. You're trying to figure out, is this thing in the kind of region that we're looking at. And I want to give you an example here of one we came across. So what we had here was one shaft which had to attach to another spinning shaft. Now, it had to be able to, the coupling had to be able to carry a certain amount of torque to be useful. However, there was a chance of a component jamming upstream. And if that happened, we wanted this coupling to fail as a safety factor. So basically the coupling had what's called a roll pin, drilled straight through the middle of it to act as a shear pin. And we tested this simply by setting up this apparatus with an inner and outer shaft, the pin through the middle. We had a digital torque wrench, but you could easily do it with a lever and a known amount of force, for example, from scales. Measure the torque that it failed at, and it gave us really good results. We got a stack of data that fell within about 10% of a mean, and for something like this, that's fine. That's great data, and not only did it give us real-world validation of our estimation, we guessed this pin would be acceptable, and it all failed as expected. It failed when it was within the safe range. Apart from giving us good, valid, hard data, it also taught us so much more, because it taught us the profile of this failure. Did it all let go in one sharp bang, or did it yield slightly as it went? And it also taught us, for example, once this component has broken and everything's still spinning around, does the pin, or the two halves of the pin, fall out and act as debris? Is it going to get caught in an oil system? Is it going to destroy other components? So just doing basic workshop testing like this, that's just an example, but it can teach you so much about the components you've so far just had assumptions and estimations for. And that test took us about 20 minutes. It didn't really cost us any money to set up, and it gave us some really useful information. So that's an example of just really simple testing you can do, and seeing that sort of testing at a competition, seeing the results of that testing and a bit of your methodology. And we know that student teams aren't loaded with money. We're not necessarily expecting top-notch instrumentation and precise, precise measuring equipment and this sort of thing. We just want to see that you've put the effort into getting good testing validation data. It's worth so much more than just coming to the competition with design theories and FEA, which, as we've said, is still theoretical. So these are all simple tests of individual components, either to check our FEA or to check the component itself. But even if we can check that all the components work well or work as expected, it doesn't guarantee the vehicle's going to do the same. So to do that, we need larger assembly testing, and often this involves field testing, the fun part of race cars. So complex vehicles, large assemblies. Some assemblies you can test in the workshop, but for the most part, if we're testing the entire vehicle together as one, we need to take it out and drive the thing. But it's not just as simple as going out and driving it until it breaks, and then fixing the bit that broke and starting again. So that's sort of endurance proof only testing. And it doesn't really meet our requirements for engineering validation. Yes, it gives you a reliable car. There's no way of arguing with that. However, this competition is about more than just winning the race because you've got a reliable car. The bigger picture of competitions like Enduro Student, Formula Baja, Formula SAE, is that you're here to learn engineering skills to be a more useful engineer once you graduate and move into a professional role. So we're not trying to get to the point where we can just say we improved the car until it didn't break, because that's not very useful to an employer. If I'm hiring an engineer and the best they can come up with is they took one system, even a complex car, and fixed it until it didn't break, I don't know that they're going to be useful to me as an engineer. I don't know that they have the skills that I need for them to do research and development for me. Instead, I want them to be able to say, we know that our methods and assumptions were correct. We knew that when they weren't correct, we fixed them, and now we know when they are correct, and this is the best car we could make. That's the point of this validation and testing, and it's sort of the larger point of these university student competitions, is to get you into the mindset of properly following through the engineering procedure. It doesn't have to be, this is the best car, because we know there are limits on budget and time and people and all these sorts of things. If you want the best car, then I assume you'll win the event. But like I said earlier, that's not really the end point. It's to get the best car you could make, and to know that it's the best car that you could make because you've validated things. So, field testing, fun bit. So, this isn't always just taking it out and driving it, like I've said, but we can do actual simple experiments, again, with field testing to get specific data. So, for example, driving the car constant speed on flat level ground, we hit a bump. It's a measured bump, so we know how big it is. We know how fast we're going, and we measure the data that comes from the car as it responds to that bump. We do that again and again until we've got a nice consistent data set. And this is because we're trying to test or validate one particular thing about the car. We might be trying to validate its suspension response. We might be trying to validate its shock absorber response on the suspension. Or it might be other tests such as straight line acceleration, hard braking, or constant speed cornering, basically driving around in a circle. And this is trying to gather data on the car to validate those assumptions and estimations that we put into the car's design right at the very beginning. We can also do field testing across a complete track, covering a wide range of terrain over a long lap. That's also useful, but for those sort of tests, we're looking at a general spectrum. We're saying over an entire lap, the car does this, or the car does that, or the car spends more time in a lap at high revs than low revs, or the car spends more time cornering than braking. It's general spectrum data that we're looking for there. So both of those have advantages and disadvantages. But all this data we're talking about, where's that coming from? How can we get useful data from a moving vehicle? And this data recording is essential for validating your design. There is not many tests that you can do from outside the car, except for maybe top speed, or you could probably judge response frequencies on the suspension from a video, but it's not great. We need onboard car data. So options, commercial solutions, for example, Motec. Yes, it's very powerful and it's quite easy to set up. However, it's obviously very expensive. It can form a large part of any team's budget if you go ahead with it. Using that these commercial solutions, it can give you really important skills within motorsport, but those skills can be less applicable in wider industries. Or our other option, this is data logging with a off-the-shelf, low-cost DIY system. For example, things like an Arduino or a Raspberry Pi, real basic, simple microcomputers. Now, obviously, these are very cost effective. They're quite cheap. The sensors for them are quite cheap. Bear in mind, with a commercial solution like Motec or something similar, often the sensors are also very expensive. Whereas with our smaller, cheaper solutions, often the sensors are really simple, off the shelf components. It can still be powerful if you can set it up efficiently. With a commercial solution, you do get what you pay for. However, so many times we see teams across many different competitions that have got far more data than they know what to do with. They can produce all these wavy lines, but they don't really know what's going on. And to be honest, I'd much rather see a team with limited data who really know it inside out and they've used it to validate their car or to learn things about their car, than a team which has recorded all the data and has no idea what to do with it. And again, this comes back to the point of the exercise is to learn about your validation and the engineering that goes into validating the assumptions that you've made. Obviously, things like your Arduino and Raspberry Pi are more work to set up. You need to get into the coding. You need to write a data logging script for it. But these are skills that can often translate to hundreds of different applications. It's amazing where in the world of engineering you find a use for just, I wish we could record this as it runs, or I wish we could log that as it runs. And if you can bring that skill to a role, it can be extremely valuable. So, field data collection, what are we going to log? There's many different channels we could, but what's useful for validating your design? We could log the driver's body temperature, and that's very interesting for certain aspects, but it doesn't have much to do with the assumptions and estimations you made when you started designing the vehicle. So we need to think of things that relate directly or can be related directly to the assumptions you're trying to validate. A good one is suspension positions. Now, the expensive way of doing that is with linear potentiometers. The cheap way is with rotational potentiometers attached to suspension components. I did this myself for a project a few years back, and while on the face of it, it seems quite primitive, it works surprisingly well. And like I said before, it's because we're not necessarily after super detailed space level data. We just want to know not roughly, but where within the suspension travel are we sitting at? How fast is it moving? How is it responding to certain things? So you can log what would seem like relatively complex things pretty simply. Other things we want to keep track of: wheel speeds, extremely useful. Knowing how fast the wheels are turning, when they are or are not touching the ground. Driver inputs. The driver's in charge of the show. What the car does depends on what the driver tells it to do. So logging your driver inputs can be very handy as well. For example, where is the driver steering? How much throttle are they applying? And how much brake are they applying? And that can actually be, it can be useful to measure the brake pedal position. That is, how much brake does the driver actually think they're applying, as well as later on we mentioned measuring brake pressures. Brake pressures is a more direct vehicle behavior, but sometimes we want to know how's the driver interacting with the vehicle, and tracking that brake pedal versus brake pressure can be really important there. Other information about the motor or the transmission, for example, belts, pulleys, etc. What speed are they doing? What temperatures are they doing? Try not to burn them out. Vehicle accelerometers. These are extremely popular in tarmac racing because they give you a lot of information about how the car's handling. Off-road, naturally, we have the problem of noise. I've done some accelerometer testing on buggies in the past. You do get a lot of noise, vibration coming up through the ground. It can be tricky to pull out useful data from accelerometers. It can be done, but you have to do some research into filtering, so noise filtering, to make sure that you don't either hide information that is useful to you or make wrong information worse. But vehicle accelerometers can be very useful. So we've got all this raw data, numbers that have come off as our Arduino or Raspberry Pi. Great. How do we actually turn that into useful things? So from our suspension positions, we can get velocities. How much is that changing over time, obviously? From that, we can calculate a lot of things. Our shock absorber forces. How long is the spring and how fast the dampener moving? There's your force. We can get some suspension forces. Lateral force, maybe not as much, but your vertical forces on things like uprights or arms is really good for validating your FEA. For example, during driving, we can calculate that our suspension arm sees between 400 and 2,000 newtons, depending on different conditions. So we can FEA to match those conditions, or we can see if our FEA was done to match those conditions, and there's your validation. Wheel weights. How much is another thing we can calculate based on our suspension positions. We can estimate it, and that'll give us our weight distribution, and particularly our dynamic weight distribution. As the car's driving, how is the weight moving around? Wheel camber, another thing of back calculating your geometry. If we know where the suspension is, what can we do with our original geometry numbers to figure out whether the car's doing what we want? We've got things like ride frequencies, ground clearance. And this is a big question that often comes up: is what sort of ground clearance should we aim for? And obviously, because it's a question you have to try and choose an answer to very early on in the design. You can't leave that choice until late, so you have to do it quite early. But then the question of, have we actually chosen the right one? And once we start driving and you're monitoring and you're logging your suspension positions, then you can see, okay, we're using most of our ground clearance, but not all of it. So we could actually lower the vehicle, either now or in future. We could lower the vehicle and have better stability, have better cornering without running into collisions. Our driver inputs, we can, for example, get our front wheel steer angles. We can compare that to the vehicle performance in terms of our vehicle dynamics. We can get tyre slip ratios. Under acceleration, how much of the back wheel's spinning up compared to the front? Should we retune our CVT or our transmission to better suit that? Or, from a validation standpoint, are the wheels slipping as much as we thought they would? Can we validate our design estimations based on what we expected those values to be? Another big one that comes up is brake pads. The brake system is often one which has a lot of theoretical thought put into it, has a lot of assumptions and estimations, but then has very little actual design validation done. And so using the data, using brake pressures, we can calculate our brake pad forces, our coefficients of friction, using our using our vehicle, using our wheel speeds, we can look at which brakes are locking up. Should we rebalance our brakes or respec our brakes, or can we validate our assumptions and estimations that were put into the brake calculations? And just one quick example there, just to show you sort of how useful even a basic system can be. So, like I said before, this was measured on an off-road buggy with the suspension, one of the front wishbones, the suspension arm, its angle relative to horizontal, was measured with a potentiometer, and then that potentiometer voltage was logged with an Arduino. It was logged at about 80 hertz. You probably speed that up with a bit more thought into the coding. And then we repeated a drive over a bump at constant speed. And what we can see here is, even though this is a very primitive system, the wiring diagram for this has four components on it. And already we've got real world data, so that's extremely valuable from a judging standpoint. It shows just how much the suspension's moving, not from driving the car around in the field and looking at it and seeing if it looks like it's moving a lot or not much. We've actually got data to show how much it's moving. From this, we can look at the frequency of it. If we know the size of the bump, then we can run a quick simulation to see whether our damping is appropriate. It also shows us other sort of related knowledge that we might not even have thought of. For example, we can see here that as the bump wears off and we go back to our normal oscillations across rough terrain, we can compare the magnitude of those oscillations to the magnitude of the bump. And we can see that, okay, perhaps our suspension spends most of the time working in the middle third of its travel, but we need the top third and the bottom third for bumps like this. Until we did this experiment and collected this data, we didn't know that. It was all based on guesses and assumptions. So this sort of thing's been extremely useful. It's just an example of how much you can achieve with a really basic system. So imagine the sort of data you can pull, look at, and get useful answers from if you log all the suspension on the car, if you log how fast it's going, and all these sorts of things. So it's really useful stuff. And it's exactly the kind of stuff that we want to see once you put some thought into interpreting it in the design judging. So yeah, just recapping there, utilizing our field data. And like I said, often the easiest ones to start with are actually our early basic vehicle estimations we made. We estimated, like I said before, what our ideal ground clearance would be. We can validate that assumption either by saying, yes, we were correct, we have got the right ground clearance, because we can see that the vehicle almost uses all of its ground clearance, but it doesn't touch the ground, therefore we're pretty spot on. We can say we made a valid estimation early on, or we can look at it and say, this value needs to change in future designs. We've modified the existing vehicle in this way and this way to address this problem. Then that's our engineering solution to the problem, and that's great stuff. That's exactly what we want to see in design judging. Once we've looked at some of those basic vehicle properties, we can then look at perhaps validating our later design choices. So examples of that, so we can start going into our brake setup, our brake balance. For example, some of the more detailed properties of your transmission, its speeds and centrifugal rates and all this sort of thing. Those choices that we made later in the process when we already had most of a vehicle design and we had to choose these smaller things, we want to still get in and try and validate those as well, as we use some of the more finer detail from our field data. And just to sort of cap it all off, so this is sort of the process that is great to see in design presentations and design reports after you've done your field validation is, first of all, this is the value we chose. This is the value we chose for ground clearance or pressure or force or how thick something has to be or whatever value it is. Number two, we chose it because, and give a good engineering reason. It can be an estimation. That's how engineering works sometimes. We estimate what the best ground clearance is going to be. We built our car to match that value, hopefully tick. If not, explain why the build didn't go as expected. But if it all went to plan, here is data showing that the value was achieved. Or if it wasn't, showing what went wrong. Why wasn't the value achieved? Why didn't you end up using that ground clearance? And what have you done to address that? Alrighty. Brings us to the end of the main presentation. Thanks very much for listening. Now, I've got a few quick questions here that were submitted that I can try and just briefly address. So there's a question about rollover stability of the buggy and the technical aspects of it. Without really having time here to get into a long explanation of it, one way to think about your rollover stability is it really just boils down to how far apart the tyres. So if you imagine standing next to a vehicle and trying to roll it over, it's just how far apart the tyres are and how high the centre of gravity is. 99% of rollover stability boils down to those two properties. And once you look at it that way, it's really just two geometry problems. It's how wide can we make our vehicle? Now, not just how wide can we make it full stop, but how wide can we make it without compromising other factors, for example, maneuverability or our ability to transport it. and how low can we make our center of gravity? And again, that's sort of an example of that is in the ground clearance problem we were talking about earlier. How low can you make this vehicle's center of gravity by keeping it low to the ground? That's a good start, without running into suspension travel problems or ground collision problems. And then within the vehicle itself, how can we keep heavy components low in the vehicle to keep its center of gravity low? So hopefully that's just a quick brush over of some of the issues and approaches for the rollover stability of the vehicle. Another question about taking into consideration the terrain conditions for these vehicles, and I guess for off-road vehicles in general. Yes, for these vehicles, it's very important to consider what sort of terrain it's going over, and in particular, the more detailed you can get, the better. Tarmac vehicles don't have to deal with this. They can usually assume that it's going to be pretty flat, apart from the odd crack in the tarmac. But we're dealing with disturbances to the vehicle. So the vehicle is ideally driving on flat ground until a disturbance comes along. It might be a drop or a bump or a vibration input driving over repeated rough ground. And these are all things that we need to get in the mindset of reducing them down to physics inputs to the vehicle. The approach angle for a bump or a jump, what does that do to the vehicle from a force body standpoint? What forces does it apply to the vehicle at the nose, at the tail? What moments does that end up resulting in? When we're hitting a small bump quickly, sorry for a second. When we hit a small bump quickly, should we be treating that as a rapid input to the suspension? Should we be treating it as a slower rise and fall on the system? And there are different ways of simulating that. So, sorry, just going back. Yeah, so the terrain conditions. Other parts we obviously have things like mud and sand, things which maybe aren't so much stressing your vehicle from a physics standpoint, but from a traction standpoint. But this still boils back to physics. It's how much force does it take to push, for the rear wheels to push the front wheels through the sand, or over rocks or up a steep hill, or any of things like this. How much traction can we get out of the rear wheels? How far should we be spinning them through sand and things like that? And perhaps here's a challenge for a team if you're looking for time to kill. If you've got time to kill, how do your tyres behave on all sorts of different terrain? Can you do some sort of controlled testing to measure the spinning of the tyre, its speed, its torque over sand, over mud, over grass, and most importantly, can you integrate that data into your vehicle's design or into your transmission design? That would be really impressive to see. I think we will probably leave it there. I'll just check one thing, if you'll bear with me. So we had a question on the YouTube about defining weld joints on a chassis analysis, and this is a good point. I'll try to sort of expand it into some broader information. So what we're sort of looking at here is, this boils down to a question of, can we take something in real life? I mean, everyone sort of knows how a welded joint looks and acts in real life. We're reasonably familiar with them. But a computer doesn't. We can't just tell the computer it's welded and expect it to understand what we're talking about. So how do we take something like this, which is, to us, is relatively simple, but to a computer it's quite complicated, this joint, and how do we get the computer to understand a simplification of this? And the immediate response to how simple can I make this thing is, how much detail do you want out of it? So for example, on something like a big lattice work bridge or a electricity power line pole made of lattice, the welded joints may not need to be in much detail, so they may be simulated as a rigid intersection with effectively beam bending coming out of them. this is really a question about how much detail do we want from this thing. On something like a chassis, we're starting to get into the realm where tube junctions can be quite important for our chassis behavior, but it still comes down to a question of, sorry, just a second. It still comes down to a question of what results do you want? If we're, for example, doing an elastic analysis, particularly with small deformations, then a purely solid welded simplification of the weld joint may be acceptable. We simply tell the computer there were 3 idealized theoretical beams meeting at a certain point, it's rigid, and away we go, and that might be enough. However, if we're doing, for example, a high detail crash simulation where an object comes in and it deforms the chassis and the tubes wrap around it and their joints are under a lot of stress and a lot of deformation, that's where our joints need to be much higher detail simulation. So I'm sort of going to turn the question of how do we define the weld joints to be how much detail do you want to get out of your analysis. And hopefully from here you can, if you don't immediately know the answer to that, then the best thing to do is to try different options. Try it with rigid joints, try it with a much higher detail. For example, a shell model of a chassis takes a long time to set up, but you may need it for particular analysis you're doing. So this sort of goes for, as a general rule, is if you don't immediately know how detailed your analysis should be, just try different things. And this goes back to the recipe and the ingredients. There are lots of recipes or tutorials on the web to showing you how to mix your FEA ingredients to get a certain result, but these people already know that a certain simplification is acceptable, and they tell you the ingredients you need to do that. It's then your job as an engineer to experiment with these different ingredients, try mixing them in different ways, try doing an elastic small deformation analysis with really detailed joints, see if it makes any difference. And go the other way, try mixing the ingredient of simple joints into the recipe of a very detailed crash analysis, and see what happens. And this is how you learn all these things. The recipes are good for teaching you the ingredients, but then you've got to go through and really try and familiarize yourself with them. So I think we will leave it there. Thanks very much for watching. And we will hopefully see you next time.